Hey guys, I'm going to try to give a fairly short video on essentially chapter 3, which is projectile motion. You'll hear some thunder in the background. It's storming right now, but so if you see me jump up, that might be because there's lightning in the immediate area. But hey, let's move along. Hopefully my computer doesn't blow up. Oh, that would suck. So let's take a look at what's going on. So we have an example here where we have a plane that is going north at 80 meters per second, and it has a tailwind, a wind coming from behind that is 20 meters per second. And if they are both in the same direction, the two vectors will add together, creating one larger vector. So in this case, we're going to have 80 plus 20, making a 100 meter per second long vector. So the plane will move 100 meters per second relative to the ground. If the two vectors are moving in opposite directions, then they will subtract. It's still technically addition, but they are in opposite directions, so one of them is a negative direction. And we will have a 60 meter per second resulting. So this is how fast the plane would be moving relative to the ground. Now if there is a crosswind, then we would have, again, tip to tail vector addition. So the tip of one, right, the tip of one vector, we put the tail of the next, and then the resultant gets drawn from the very beginning to the very end. And in this case, I have an 80 meter per second vector of the plane with a crosswind of 60 meters per second. Is this realistic? No, planes typically will fly faster than that, but nonetheless. So the resultant would be 100 meters per second. We would use the Pythagorean theorem to figure that out. So, and then what about the angle? The angle, we would use a little bit of trig, so SOHCAHTOA. The sine of an angle, this is the symbol theta, that represents an angle. So the sine of theta is equal to the length of the opposite side divided by the hypotenuse. Cosine of the angle theta is equal to the adjacent over the hypotenuse, and the tangent of the angle theta is equal to the opposite over the adjacent. So, as an example, since this was my original data, the 60 and the 80 for the opposite and adjacent sides respectively, let's start with that. So if I want to figure out the angle, okay, I know that the tangent of the angle is equal to the length of the opposite side over the adjacent side. So that's going to be 60 over 80. To figure out the angle though, what we do is we take the inverse tangent of each side, and it will look like this as a result. So the inverse tangent to the negative 1, sorry if that's not super clear, but that's tangent to the negative 1, that's the way it's written, of the opposite over the adjacent. Let me put parentheses over that. It is very good to put parentheses around it as a habit. And that's going to equal the angle theta. So let's go ahead and put that into our fancy calculator. In fact, let's go ahead and expand this guy here, and we'll have to turn that calculator on. Okay, so let's do that. Let's see if I can get this guy on my screen. Okay, and there it goes. So we're going to take the, let's see, here's the inverse tangent of the opposite, which is 60, divided by, and in fact I can even move this calculator over here so that we can see it. So the 60 divided by, let's see, 80. So let's see if I can do that. The 80, close my parentheses. So inverse tangent of 60 over 80. And that is equal to 36.87. So there is what we've got right here. Okay, good, awesome. Let's see if I can put my calculator away now that I've done that. Whoa, I put it away all right. So now I've figured out my angle. I could use the hypotenuse to do that, but alas, I don't really need it. It's better to go back to my original data if possible. So that's a real quick little snippet of how to find the angle, quick little trig lesson there. The important part though here is the concepts and what's happening. Typically speaking, if you are in a plane that is going out west versus coming back towards the east, then coming back to the east is usually going to be a shorter trip in terms of time, because the jet streams that go from west to east, they kind of come down from Canada and sweep towards the east. a plane is able to go with the wind like this here, and it would be much faster to go from California to New York than it would be to go the other way around, going against the wind. So that'll make a big difference in the times. So just to kind of go through some more examples of adding these vectors in 2 dimensions. So again, here's a one-dimensional example, a 5 meter vector, a 3 meter vector, and then we have the resultant goes from the very beginning to the very end, and that would be a 2 meter vector. If we have them at right angles to each other, and with regular physics, that's typically what I'll give, not always, but typically. We have a 5 meter vector, a 3 meter vector at right angles, so the Pythagorean theorem would give us the 5.8. So the Pythagorean theorem being the a squared plus b squared equals c squared, and c being the hypotenuse, so we would want to solve for c. So c, the hypotenuse, is equal to the square root of a squared plus b squared. So how is it that I came up with the 5.8? So let's get out the handy dandy calculator again, if it'll let me. I flipped my calculator. I didn't know that was possible. That's awesome. Haha, look at that. That's fancy. Learn something new every day. So learn something new every day. Okay, that's a cool trick. I didn't know I could do that. So okay, so how do I do that? So let's actually move this calculator off to the right side so that way we can see what we're doing. I'll even cover up my face. That's fine. Or you know what? That's even bothering me. Okay, there we go. That's better. So a squared plus b squared equals c squared. So I'm going to take everything inside of the radical. Okay, I'm going to take everything inside of the radical, and then I'm going to apply the square root at the end. So it's going to look like this. So a squared, let's just say that's 3. So 3 squared plus 5 squared. And I'm going to hit the enter button, gives me 34. And now instead of taking the square root, I'm going to go to the power of 0.5. I find that to be easier and more consistent across different calculator platforms. And so there's less mistakes that are made. I prefer to take the square root, go to the power of 0.5. Works, does the same thing. And 5.8 is our answer. There we go. Okay, so there's that. Okay, let's put this guy away again. This time I'll make sure not to flip and reverse it. All right, so let's see what else we can move on to. So let's kind of go over some more examples of vectors. So in this case, I have a vector problem where we're going to start here and then we're going to end here. Okay, and in fact, instead of using a star, how about X marks the spot? And so what I want you to recognize is that I have the same vectors here. So what I'm going to do is I'm going to, again, let me go ahead and put a star, right? That's going to represent my starting position. And I can take any single one of these vectors and start it off. So I can then tip to tail, add these vectors together. And then at the very end, how about this? X marks the spot. And I'm going to draw a resultant vector going from the very beginning to the very end. Okay, and just for good measure, how about if I make it red to represent my resultant? And so if you notice, it does not matter in what direction I put these, or what order rather I put them. So this time I'll start with that one, tip to tail, tip. Look at that, tip to tail. Or I could have switched these two around. It doesn't matter. As long as I follow the rules of going tip to tail, I will always begin and finish in the same spot. Okay, so let's kind of move on to projectile motion just a little bit. So what is the relevance? And in fact, you know what? Before I go into projectile motion, let me hit a concept here. So just so we are all clear. Velocity vectors can be added just like displacement, just like any other vector. So these arrows that I'm drawing could represent a displacement. It could be, oh, okay, this person had gone northeast 3 meters, and then they went directly east 6 meters, and then they went sort of southwest 2 meters, or whatever to scale relative lengths of these are. Where did they wind up? And this would give you a visual representation, and you actually can also do it algebraically as well, which I will have as a separate video. You can do it with velocities. So if you were on a conveyor belt, that was suspended in the air in an airplane, and you're walking on that conveyor belt, so you can have all these different directions to kind of add together. It would be a far more convoluted scenario with velocities than it is with displacements, but nonetheless, any vector you can add together. Okay, next idea of now moving on to projectiles. So the idea behind projectiles is that the vertical, up and down, and I will typically express the vertical as the y direction, the vertical y direction. That is completely independent of the x or horizontal direction. And so what I want to express here is, in this example, we have the motion of a ball that is just simply dropped. And we have position 1, 2, 3, 4, and 5. And so the time intervals are the same for each of my little drawings here. So in this case, the object is at the top for a longer period of time, and as time goes on, it starts to create a larger separation. So that's what I tried to express. If I then also have an object that's rolling off of a table and initially has a velocity moving perfectly horizontally, there's no vertical or y component velocity at all, and it drops at the exact same time, then the two objects will have the same height off of the floor at the same time. Okay, same height at the same time. Gravity will affect the y component, the vertical component, equally between the two objects. It does not matter how fast this object is moving. This object could be going 1 meter per second, 10 meters per second, 1,000 meters per second, 10,000 meters per second. For the most part, it wouldn't matter. It would still hit the ground at the same time. I am lying a little bit there at the end, because at some point in time, specifically at 10,000 meters per second, you would have to very much so start to take into account the curvature of the Earth. But if the Earth wasn't curved, if it was flat, and if you did believe Kyrie Irving, then it would not matter. So the curvature of the Earth is the only reason why there's a little bit of a caveat there to that example. Okay. Okay, so let's kind of hit one other idea. So if a projectile is launched at some sort of angle, so this arrow represents the initial motion of a projectile being launched. So what I would do is I would break down the motion of that projectile into its x and its y components. So these dotted lines just simply represent the x and y components of that velocity. Let me see if I can make this a little bit neater. There, that makes me feel a little bit better. So let's kind of label these. So the way we would label this is we would say that this is the initial velocity, or it's often actually written as v sub 0, and it's said as v naught, meaning the initial velocity. In a regular basic level of physics, we'll usually express it this way, v sub I for initial velocity. So let me just kind of erase that, and we'll express it this way. So the initial velocity. Now, this is the initial velocity along its path. This part down here is the initial velocity in the x direction. This part down here is the initial velocity in the y direction, the vertical direction. And so here's what happens to this projectile as time progresses. So it's going to have a parabolic path. So it's going to track, and it's going to go, and it's going to go up, and it's going to come back down and have some sort of parabolic path. As it goes, it turns out that the horizontal velocity of this projectile the entire way will be the same the entire time. The horizontal velocity of it will be the same. That never changes. So for example, let's say, let me make another identical arrow just like this. So what if this arrow here, okay, in fact I'll even, let's see if I can even change the color of it. So what if this arrow here represented the velocity of you running. Okay, so here you are running at this velocity, and your friend throws a ball at this velocity, at an angle. It just so happens that your velocity in green is the same as the horizontal velocity, the x component of this projectile. So the moment that you run by your friend throws this object. As the object goes up into the air, right? So we'll just make a ball of some kind. So as the object goes up into the air and it goes, that's not what I meant. There we go. So as the object goes up into the air and it goes and it tracks, you would be running underneath, and the entire time you would see that object directly over you. And in fact, if you were to maintain the same velocity the entire time, and I know that my head's in the way, how about if I move my head? I'm just gonna move myself somewhere over here. So if your velocity, all right, is maintained the entire way, then this object will be above your head the entire way, and you'll catch it, right? It'll land right in the bread basket. It'll be a good touchdown. Spike the ball the whole bit. So the horizontal velocity of the ball never changes. What does change is the vertical velocity of the ball. Okay, so as time progresses, as the ball is on its way up, the velocity of the ball decreases on its way up, right? It becomes very small, in fact, really zero at the top. And then on its way back down, if it'll let me, the velocity of the ball increases in the vertical direction, right? It increases, and then when it comes back down here, it will have the same vertical velocity downwards that it initially had going upwards. Okay, so this velocity going up should be the same but opposite to this velocity going down, right? You can kind of get that feeling. But the horizontal velocity never ever changes. If you were running across the bottom of it, you would see it above you the entire way. It would just be going up and down in your perspective. Okay, tell you what, I think that we will leave it at almost that. Let's do one more quick little example. If you were to throw a ball, what angle would be the angle that would allow for the greatest displacement in the x direction? What would create the largest range? Then the answer to that question would be at 45 degrees, right? So 45 degrees would be an angle that looks pretty terrible, but excuse me for it. So 45 degrees would create would be an angle at which, as long as you're starting and finishing at ground level, right? If this is all ground level, then 45 degrees would be the angle. However, if you wanted to throw it at any different angle, let's say you decrease this slightly to 44, right? It would be just a tiny bit less. So just a tiny bit less doesn't go quite as far, right? It obviously must. What if you went to 46, right? So you've already gone 1 degree below 45, now you're going to go 1 degree above 45. So instead of 44, right, the red one, that was 44 degrees, now let's do 46 degrees. So we've gone above 45 by just a little bit. That is actually going to hit the exact same spot, okay? 46 and 44 will add up to 90, and they are complementary angles, and they will hit the same spot. So you could throw one at 46 degrees first, and then throw one at 44 degrees just a moment after. They would both hit the same spot. The same is true of 89 degrees, right? That would go way up, 89 and 1. And that's an old snowball fight trick from middle school, right? Throw one high, the person you're throwing at looks up, and then you throw one low. Try it. Good times. So I think that'll do it for now, and I'll elaborate on some more things at another time. We'll definitely elaborate more, and so with that, we'll leave it. Good intro. Have a good one.